Hopefully you guys have had a ton of fun playing around with verifying some new trigonometric identities and just seeing how that stuff works. What we're going to do now is we're going to build some very specific ones. Some of these are going to be very hard to come up with. For instance, the first one in this video is going to be a really difficult thing to do. So honestly, I'm not going to show it all. I'm going to give you some hints on how it works, and then I'm just going to direct you to a really nice write-up in the text. And if you'd like to see where this comes from, you'll be able to find it pretty well there. I'll explain the main details of how this comes up, but I'm not going to show all the steps. But then what we'll be able to do is use that first formula that we get, that first little identity, I guess you could call it, and we're going to verify a whole bunch of other ones. So that'll be really nice. And then what we'll be able to do is use those formulas to find different exact values for angles that we haven't messed with before. Right now, the only angles that we're really able to play with are 30 degrees, 60 degrees, 90 degrees, 45 degrees, and then all the multiples of that, right? Put them in any quadrants, and those reference angles are good. Or if we're thinking about radians, you can say pi over 6, pi over 4, pi over 3, pi over 2, and all the multiples of those. So we really don't have any way of looking at an angle like pi over 7 or 15 degrees and knowing the exact value. Those weren't the same angles, by the way. I'm just making two up separately. And knowing the exact values of like sine of 15 degrees. Soon we'll be able to build up to things like that. So we're going to be able to do that. We'll also be able to use the formulas to, like I said, verify some new identities. Some of them will be very helpful. Some of them will be just random things that we'll mess around with. So that's what we're up for today. The main bulk is going to be showing off these sums and difference formulas. We're going to be thinking about differences in angles. So here's the first one. I'm just going to give this to you. I'll show you the main idea for how this works, but first let me explain what this is. So we're going to be looking at cosine of a difference of two angles. Alpha is one angle. That's this right here. Maybe I should show that. And beta is some other angle. Normally we use theta to represent an unknown angle. If we want to use a bunch of angles all at once, we'll use alpha and beta and gamma and things like that, because those are the Greek letters that normally align with like A, B, and C. Anyways, Greek letters are for angles normally, whatever. So what this is we're really looking at something like, if we wanted to find cosine of 15 degrees, we could say, well, what if alpha is 45 degrees? And beta is 30 degrees. Those are two angles that we know. And notice then that we just get some trig functions of those separate angles. So if we can come up with a way to break these into their little separate angles, and we know what those are, then we can figure out cosine of the difference of those things. The way this formula comes about is by looking at two pictures. I'll do my best to draw them. Our textbook has them really nicely, but I'll do my best. So we're going to draw the unit circle here. And I'm going to draw two angles. It's not very good, but oh well. My first angle I'll do in red. My first angle is alpha. My second angle I'll do in blue. I'm going to pick a lighter blue. There we go. And this angle, all the way up there, is beta. It's not a very good beta. Let me try that again. That's still not very good. There we go. That's a better beta. So if we take a look at these points, maybe I'll use red for this point, and I'll use blue for this point. The coordinates of these on our circle are cosine beta, sine beta, because we know that on the unit circle, the x value of the point is the cosine output, and the y value of the point is the sine output. So similarly, this point here is cosine alpha, sine alpha. And then what we can do is we'll draw a straight line connecting these two things. And we'll say, what's the distance there? I don't know. It's some distance formula using these coordinates. We know what the distance formula is. We can do that. Then what we can do is say, well, let's draw a second picture. And what we're going to do is we're going to create another unit circle. So we'll see if I can draw a decent circle. Oh, this is already starting off poorly. Let's scrap that and try it again. Not great, but oh well. And at this time, we're going to shift alpha. And we're going to make alpha 0. So at this point, we know what the coordinates are. It's 1, 0. And then we're going to shift our beta angle around by the same amount. So let me try and kind of guesstimate it here. That's going to be like right there. And this angle isn't beta anymore. It's beta minus alpha. So what you'll notice is we've just taken this picture and we've rotated it around, right? We're just saying rotate it a little bit this way until alpha touches down here. And what we'll notice is that this line, this orange line in between these 2 points, is the exact same length. Why is that interesting? Well, because now the coordinates right here are, oops, I need to get rid of my straight line. Cosine of beta minus alpha as our x coordinate, sine of beta minus alpha of our y coordinate. And so if we take a look at the distance formula between here, we'll be able to get a distance for this orange line, set that equal to a distance of this orange line, and then you can solve for cosine alpha minus beta, and this is what you'll get. The textbook does all that work in between, but this is the main picture of what we've got. So we drew 2 angles, alpha and beta, and then we just turned the whole thing, that whole picture, until alpha is 0. And this new angle here, beta, is just beta minus alpha, because we turned that just the same amount. Anyways, take a look at the textbook to see that if you'd like. But what we're going to do is we're going to say, this formula right here, we believe it. We have this for us. Let me get this nice straight line on here instead. All right, this formula that we've got is something that we believe. We're going to use that. So we're going to derive other formulas from it. There's a lot of information on this page, so just go through it slowly with me. What we're going to do is we want to find the other formulas for sums of angles in the sine and cosine function. Right now we have a difference of angles, right? Subtraction sign right in there. We want to be able to add 2 angles together. And then we also want to do it for the sine function. We want sine of alpha plus beta and cosine of alpha plus beta. Then we want to find a formula for the difference in angles again, alpha minus beta, but for the sine function. So if we do that, we're going to have all 4 possibilities. Adding angles together, whether it's sine or cosine, and then subtracting angles, whether it's sine or the cosine one, which we already have. And here's the general strategy, and we'll do this. You can follow along with me. For the sum of angles ones, we're going to make the second angle negative. So we're going to subtract 2 angles, but we're going to say, you know what? The second angle is really just negative beta, where beta is the positive version of it, toss a negative sign. Now, when you subtract, that becomes cosine of alpha plus beta. And we'll just go ahead and substitute negative beta into everything. And there you go, sum of angles. We can do the similar kind of thing for the sine function if we had the difference of angles for the sine function, but we don't have that. So instead we're going to use this nice little complementary angle co-function identity thing that we have, where if you remember, if you look at the triangle, if this is theta, then that's pi over 2 minus theta, and sine and cosine of those things are the same because they're referencing the same sides of your triangle. So then we'll go ahead and we'll switch that cosine formula over to the sine function. So what we're going to do is we're going to let theta be alpha plus beta. So then sine of alpha plus beta is really cosine of pi over 2 minus alpha plus beta. And we'll group some stuff up and do a whole bunch of things. For the difference then, if we have the sum of sines or sum of angles for the sine function, let me get that again. Then we'll say, hey, what if we just make beta negative again? Just like we did up here to get the sum one for the cosine. If we switch the sine of beta, then there, difference, done. So that one's going to be really easy. So let's work through this, and we'll keep these strategies on our page. So here's our sum of angles for the cosine function. So we have this, again, this is our known one that we've got. This very first line. Difference of angles for the cosine function. And what we're going to do is we're going to take every beta on here, and we're going to switch it out for a negative angle. So there, and there. We're going to swap those out for negative beta. So now we have cosine of alpha minus negative beta. That's really alpha plus beta in there. So that's good. Cosine alpha, cosine negative beta, plus sine alpha, sine negative beta. Cool. Wait a second. Where'd the negatives go? How come these signs switch? these are even and odd identities. So notice this. I'm just going to write this real quick over here to remind you. Cosine is even. Sine is odd. Oops, that said off, like some sort of idiot would type. Anyways, here we go. The cosine function is even, which means cosine of negative beta is equal to cosine of beta. And the sine function is odd, which means sine of negative beta equals negative sine beta. So there's this negative sign floating around here. Isn't that kind of cool? We can use that even and odd symmetry stuff. Like I said in the last video, I think you're probably not going to use these a lot on your own, but we'll use these together. This is a really important spot that we'll use this, where we can get this new sum of angles formula. And again, we've got a sum of angles, but we've broken it down into just the component parts. So now, if we wanted to, for instance, look at like cosine of 75 degrees, instead of 15 degrees, then instead of subtracting 45 degrees minus 30 degrees, we can say, well, what if we looked at 45 degrees plus 30 degrees? And we can figure out what that is too. And we'll do that kind of thing later. Let's do the one for sine. I think I probably meant to break this up into a couple of pieces, but oh well. Let me just show it all here. This is a lot all in one slide, but whatever. So we're going to use the fact that sine of alpha is equal to this cosine of pi over 2 minus alpha. That's our whole complementary angle business. We've worked with that a couple of times already this semester. So we're going to switch things over. So all of this stuff is still going to be true. So now what we're going to do is we're going to say sine of alpha plus beta is equal to cosine of pi over 2 minus alpha plus beta. Same thing is right here. Then I'm just going to distribute this negative through. So that's why I have minus and minus here. And then I'm going to group these two things up. Pi over 2 minus alpha minus beta. So now we have a difference of two angles and a cosine function. One of the angles is pi over 2 minus alpha, whatever that is, and the other angle is beta. So we're going to go back to, so this is just starting a new page over, so all the same stuff here. Except for this stuff. There we go. We're going to go back to this, maybe I'll go find it. This formula, this gold standard that we have. If you've got it written down, you can refer to it. Or if you've got your textbook, you can refer to it. So we're going to go ahead and we're going to put pi over 2 minus alpha in for one angle, and we're going to put beta in for the other. So instead of cosine alpha and sine alpha, we're going to have some other stuff. So here it is. So instead of cosine alpha, we've got cosine of pi over 2 minus alpha. And instead of sine alpha, you've got sine of pi over 2 minus alpha on here. But notice that these are really complementary angles. We can switch the function over, just like we did originally, right? So cosine of pi over 2 minus alpha, that's just sine of alpha. Sine of pi over 2 minus alpha, that's just cosine of alpha. You guys have had those little identities kind of locked and loaded, right? So there we go. Sine alpha, cosine beta, plus cosine alpha, sine beta. We just switch these functions over, and now they're just in terms of alpha. So here's our formula. Sine of alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. Now we can do the same kind of 75 degrees as 30 degrees plus 45 degrees, but we can do it with the sine function. So that's pretty neat. And then lastly, difference of angles. We're going to do the same thing that we did earlier. We're going to say, hey, beta could be negative. Let's just make them all negative. So we're going to take all of these betas and we're going to switch them out for negative betas. So bang, 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 there they are. And then again, we're going to use the symmetry argument. We're going to say, well, cosine is an even symmetric function. So cosine of negative beta is really just cosine beta. Sine is an odd symmetric function. So sine of negative beta is really negative sine beta. So you're going to see this sine switch right here. Did I not put it in? Oh, there we go. There it is. So there's that sine switch. So sine beta now, but there's a negative here. This is now cosine beta. It's still positive because of that even symmetry. Everything works out real nice. So here's our quick summary. We've just shown 4 different formulas, all coming, well, I guess 3, coming from one that was just given to us. So reminder, this one we never really showed. Oops, I want my highlighter. Bang, there we go. This one we never really showed. You can find that in the text, though. Once you have this one, you can get all these other ones. You will probably not have to recreate that from scratch, but you can assume that I want you to know the general idea behind how we convert from this second one here to all the other formulas. So keep an eye on that. Make sure you kind of understand some of the little ins and outs there. All right, so how can we use these? Well, first we can use them to find some exact values like we talked about. So here we go. Sine is 75 degrees, and I've already given you this hint. Hey, 75 degrees is 45 degrees plus 30 degrees. So let's rewrite this. Let's rewrite this as sine of 45 degrees plus 30 degrees. And now go back up to here and say, hey, look at this. That's this formula. Alpha is, what did I write? 45. Beta is 30. Go ahead and plug all that stuff in, and you're going to get some known values out of this. Pause it if you want. Try and work yourself a little ahead. Get right to the end of it, and then I'll kind of walk you through the rest of this stuff. Are you done yet? Did you pause it? Are you back? All right, here we go. So, just like I said, let's rewrite this. Sine of 75 degrees is really sine of 45 degrees plus 30 degrees. And there we go. Sine alpha, cosine beta, cosine alpha, sine beta, where we're saying 45 degrees is alpha, 30 degrees is beta. These formulas are kind of hard to memorize, so I'll give you a hint. You're not going to need to memorize them. I'm going to give you a sheet that has these formulas on them. Isn't that so nice of me? I know. It's incredible. Anyways, here you go. Sine of 45 degrees. We should know what that is. If not, let me draw your little triangle here. We've got some side lengths of 1, root 2. So, if this is 45 degrees right here, sine is 1 over root 2. Then, we can say cosine of 30 degrees. We should know that one. Here's 30 degrees right here. This is 1, 2, root 3. So cosine is root 3 over 2. And then you can find cosine of 45 degrees. That's 1 over root 2. And you can find sine of 30 degrees. That's 1 over 2. Just like this. So we get all these values. We should know these by now. These should be just like ready to go, whether we're using those right angle things, or if you wanted to go back, I can just draw it here. No big deal. I'm not going to draw the whole thing. I'll just sketch the picture to remind you. Our favorite friend, our unit circle. We know where these angles are. Sine, we're talking about the y value. Cosine, we're talking about the x value. Cosine, x value of 45 degrees. Sine, y value of 30 degrees. So just plot those things on here and see if you can find those coordinates. Root 2 over 2 times root 3 over 2. That's numerators multiplied together. Root 6 over denominators multiplied together. 4. Root 2 times 1 is root 2. 2 times 2 is 4. So there's our second term. If you had 1 over root 2's on these, and you'll get a different answer, but it's the same thing, just written in a different form. So if you add this stuff together, common denominators already, oh, thank goodness, it's just root 6 plus root 2 over 4. I don't know what this is as an approximation, but you can plug it into your calculator and figure it out. But that's what sine of 75 degrees is in its exact value, which I think is really cool. If you did this with the 1 over root 2's, you're going to get... that'll be root 3 over 2 root 2 plus, let me actually write this all as one thing, plus 1, I think. Yeah, it'll be something like that, I think. Double check me on that. But those are the same thing. Neat. All right. Here's another one to try. Find cosine of 7 pi over 12. And I'll give you this hint. Note, pi over 3 plus pi over 4 is equal to 7 pi over 12. So you can do the same thing, except your formula is going to be different because we're looking at cosine now. It's still a sum. So we'll go back up here and we'll say, here's our cosine, one of a sum. It's going to be cosine alpha, cosine beta minus sine alpha, sine beta. So figure out which one of these you want to be alpha, which one you want to be beta, and just start plugging them in. These are known angles, meaning we know the sine and cosine outputs. Give that a shot. We can also use these, although it's a lot less often, but we can also use these to verify some identities, just like we were doing before. So maybe we'll get some identity that involves a sum or a difference of angles, and we can use these formulas to break that thing apart. Let's see what it would mean. So let's verify this identity. Cosine or sine of alpha plus beta over cosine alpha, cosine beta plus tan alpha, tan beta. We're going to start with the left side because it looks most complicated. And you'll just notice that there's really not much that we can do. So let's go ahead and break this sine alpha beta or sine alpha plus beta apart. So this is our identity right here. You can go look it up because, again, you don't need to know this. I want my highlighter yellow, straight line, because I'm too jittery right now. And these are just given to us. Once you notice this, you can go back to our other kind of default settings stuff, and you can say, well, I've got some sort of an upside down triangle here, right? There's a nice little plus sign adding these two things up. So I'm going to look at splitting this fraction up into a couple of things. So there it is, sine alpha cosine beta over cosine alpha cosine beta. So bang, these cosine betas are gone. And then same thing over here, cosine alpha over cosine alpha. So now we've got sine alpha over cosine alpha. Well, that's literally the definition of tangent. And sine beta over cosine beta. And again, that's the definition of the tangent function. They're just two different angles. So there we go. We cancel those things out. We're left with these tangent and tangent and tangent function. And so as stated, there we go, tan alpha, tan beta. That's really what we've got. I know that was kind of another quick video. These formulas are mostly going to be used for finding some exact values in this case. Later on, we'll use them for other things in the middle of important calculus work or things like that. I can think of two instances off the top of my head in Calc 1 where you do need these formulas. And so whether you have them memorized in Calc 1 or not, it shouldn't be a big deal. You can probably look them up whenever you need them. For this class, you will not need to have them memorized, but you should know how to use them, when to use them, which one to use, etc., etc., etc. Get some practice with finding some exact values. Hopefully this is opening up a whole world of possibilities. I know some of you are probably a little frustrated up until now because we know a bunch of these exact values, but we only know them for certain angles, right? We're stuck with that pi over 6, pi over 4, pi over 3, etc., etc., etc. Really, we're just looking at multiples of pi over 6 and pi over 4 in that case. And so now we just have a lot more opportunity here. We can look at things that aren't direct multiples of those two angles. That should be exciting. We can get some good exact values of things. You can be kind of clever about how this works too, which is pretty fun. Anyways, I'll leave you there. Jump into some examples, mess around with some of that, and hopefully that goes pretty well. Let me know if you have any questions. Good luck, everybody.